Welcome! In this video, we're going to introduce the idea of the derivative and talk about how it's a rate of change. Many physical measurements change as their condition changes. For example, objects move with respect to time. The revenue that a company obtains during a month changes with respect to the number of items that they sell. The mass of a tree changes with respect to its height. A derivative measures the instantaneous rate of change. And when we graph the dependent variable with respect to the independent variable, the derivative corresponds to the slope of the tangent line at a given point. I want you to consider the following experiment that I ran. Drop a plastic ball from a window, and this window was 17 feet high, where the ball was dropped. I then recorded a video of the falling ball using my phone. A video corresponds to capturing a sequence of images, which we call frames, at equal intervals of time. Then I can capture each of those frames, look at them, and measure the height of the ball in each frame. And the question I have is, based on that information, how fast is the ball falling? Here are three sequential images from my video. We're going to be focusing on this center time, when the height of the ball was 8.3 feet above the ground. My video shows that it was recording at 29.76 frames per second. From that, we can calculate how long it was between each frame. So if I have 29.76 frames per second, then I can interpret the reciprocal of that, 1 over 29.76, as the number of seconds per frame. And this is how much time takes place between each frame. So my increment of time between these frames is 1 over 29.76, that's in seconds, which is approximately 0.0336 seconds. So this is going to be the amount of time that passes between my frames. Now, I want to think about how do I measure a rate of change? Well, a rate corresponds to a ratio of the changes. So here it's going to be the change in height divided by the change in time. You might also remember this from the idea that velocity is the distance traveled over the time it's passed. All right, now we're ready to estimate our velocity. So notice that because of the accuracy of my data, I don't have really precise information. I can see that my ball has fallen 0.7 feet in both of these increments. If I use the first 2 points, the change in my height is my end height minus my start height, which is negative 0.7 feet, and the change in time is 0.0336 seconds, and so my rate, which is delta h over delta t, the change in height over change in time, is going to be negative 0.7 feet divided by 0.0336 seconds, which gives me a velocity of negative 20.83. Here the 3's repeat, but I'll round it because I don't really have that many digits of precision, feet per second. Now, why is it a negative? I get a negative velocity because my height is decreasing. I'm going down in height. Now notice if I use the other 2 points, I would get exactly the same calculation. In reality, the ball is speeding up, so I should have, if I had better accuracy in my measurements, I should be able to see that I fell further in the second increment of time. Notice that the units for my velocity are the units of my height, that's my numerator, divided by the units of my independent variable here, which is time, in seconds. So it's feet for height, seconds for time. All right, so this is how I would calculate the speed or the velocity of my falling ball. I shouldn't have said speed because speed is technically the absolute value. The speed is the absolute value of my velocity, and so it's falling at a speed of 20.83 feet per second. I have a velocity of negative 20.83 feet per second. Now I want to emphasize that this is not the instantaneous rate, this is what we call an average rate of change. And the reason for that is I'm using 2 data points in order to calculate that rate of change. All right, I took the data from my video and I took every other frame and I plotted the height of the ball that I could measure from my data. And you'll see that I had this curve. And what we were actually calculating last time is we were calculating the average velocity that corresponded to a point in the middle here. And we were calculating this slope. And so here we found that my slope, which was my rate of change, was negative 20.83. And what you can see is if I had chosen different time intervals, I would have gotten different calculations for those average velocities. At the top, right when I'm starting to fall, we can see that we have very shallow slopes corresponding to a small rate of change, small in magnitude. And the longer I wait, the faster the ball is falling so that I'm able to get a larger velocity, so I have a higher rate of change. Because I'm using 2 different points and the ball is speeding up, I actually am just getting an estimate of the speed. If I wanted to get a more accurate speed, what I would need to do is I would need to increase the resolution of my data. I'd need to capture more frames per second so that I could get a better estimate. What that corresponds to is reducing the increment of time that I had. And so if I want better estimates of my velocity, I need smaller delta t's. I need faster frames per second so that I get my data points need to be closer together if I want to get a better estimate of velocity. And of course, I also would need much more accurate data because I just have too much error here. Well, an alternative way of getting a better estimate is instead of using data, I might try to find a formula. So I asked a spreadsheet program to take my data and find a curve that matches my data as well as it can. I chose a quadratic polynomial, so degree 2 polynomial, and asked for the formula that it used. And so I have here a parabola that does a pretty good job of matching those data. And the advantage of a formula is if I'm interested in that same point that we did our observation at earlier, we were using data points that were spaced about like this, and if I wanted to have a better estimate of my rate of change at that point, then what I could do is I could use the formula to find data points that I wasn't able to measure experimentally. And by choosing those smaller rates, I can get a better and better estimate. When we were calculating an average rate of change, remember that's where we took 2 data points and we found the slope between the lines. This is something that we call a secant line. It's sometimes also called a chord between the data points. And the slope of the secant line measures the average rate of change. When I want to know the instantaneous rate of change, that corresponds to finding the tangent line. And so a tangent line corresponds to what would I get if I were to draw a line that matches the curve at this point. So I want to be similar, I want to have the same slope as the curve at this point so that no matter how small I went in for my delta t, so if I choose delta t small, I want my line to match the curve. Okay? So at different points, I have different slopes. If I took a second point and I said, what's the tangent line? The tangent line needs to match the slope near this point. So if I were to draw my tangent line, it should match the curve of that point. It should touch. It needs to touch the curve at the point I want, and then it needs to match the curve as well as it can in between. We can see that the slope is becoming more and more negative, corresponding to my ball falling faster and faster. And so the slope of my tangent line is what we call the instantaneous rate of change. And so we give this a name, and that name is the derivative. Symbolically, where we were talking about the average rate of change being the change in height over the change in time using a Greek letter delta. So where we're talking about the average rate of change of coming from a secant line, we use the Greek letter delta to represent a change. So we have the change in my height divided by the change in my time. When we talk about the derivative, we change our notation. We use letters d instead of delta. And so the derivative is dh over dt to represent the instantaneous rate of change. I wanted to introduce another example of a rate of change and use it to connect to our idea to the derivative. I went to a website, plotterout.com, and figured what would it take to travel from Memorial Hall to Festival on JMU's campus, and it had this cool feature that it allowed me to find the elevation every so often along the route. And so here's a graph showing as I take a distance from Memorial to Festival, what's the elevation that I'm standing at. And in particular, this low point right here is the bottom of the hill at Village. So this is the bottom at Village. And the second point is at the crosswalk at the top of the hill. And so I might be interested, well, what's the average rate of change? I could take the height difference. So here I could calculate the height difference. So let's summarize some data. All right, at the bottom of the hill, we have traveled 1.29 miles, and we're at an elevation of 1,312 feet. At the top of the hill, we have traveled 1.45 miles, and our elevation is 1,358 feet. So if I name my variables d for distance and e for elevation, then I can calculate my average rate of change, the change in elevation, that's my dependent variable, divided by the change in my distance traveled, that's my dependent variable. That will be equal to the ending elevation, 1,358, minus my starting elevation, 1,312, divided by the ending distance traveled, 1.45 miles, minus 1.29 miles. And my units, again, it's feet in elevation, miles in distance traveled. And so my average rate of change is equal to 46 feet for every 0.16 miles, which equals 287.5 feet per mile. What we've calculated is an average rate of change. We're measuring the rate of change going from one point to another point in my data, and we found the slope of the line joining those 2 points. Now this particular part of the walk, and you can see from the graph, it's much steeper at the beginning, and near the end it's not quite as steep. So when I'm talking about an instantaneous rate of change, I'm not looking at the rate of change between 2 points far away. I want to know what's the rate of change right where I am, right as I'm walking. So my instantaneous rate of change, the derivative, we don't want to calculate the instantaneous rate of change by looking at 2 points far away. Instead, we want to look at points that are much closer. So for example, the 2 closest points that I could pick would be the first 2 points. And so here, we already have the elevation at the bottom of the hill. The second point, I'm traveled a distance of 1.34 miles, and my elevation at that point is 1,329 feet. So if I use this with my my point, the first point that I had, the bottom of the hill, I would have a better estimate, but again, it's not exact because I don't have my elevations changing it at different rates at different points. What I'll have is at my ending elevation, 1329, minus my starting elevation, 1312, and divide that by my ending distance traveled and my starting distance traveled. And this is still feet per mile. My estimate for my instantaneous rate of change is going to be much closer. And I get that my rate of change, and again, this is technically an average rate of change, but it's a better estimate of the instantaneous, is 340 feet per mile, a bit steeper than we had overall. When we have a graph and we want to estimate tangent lines, we've already talked about how we draw a tangent line. It needs to be a line that matches the graph at a point by going through the point and having the same slope. What I want to do is I want to illustrate that when we have a graph and we draw our lines, we can actually estimate the slope of the tangent line directly. All right, so I have a graph, and I'm going to focus on a particular point where I can measure my point fairly accurately. So I've got a point here at 8, negative 320. And I want to estimate the slope of the tangent line at that point. In other words, the derivative. So we want to know what is the derivative, the change in y over change in x, at this point. And I use this vertical bar to mean I'm calculating the slope of this point. All right, in order to estimate the slope of this tangent line, what I'll do is I'll draw a tangent line. I like to actually use a straight edge, so I'll bring a line in, and I need to draw a line that goes through the point and matches the slope. So if I were to zoom in, and let me zoom in, so you can see I'm maybe a little bit off on my graph, but the key is I want to have this slope match this part of the graph. You don't want to cross it at an angle. You want to match the graph. Once I've drawn a tangent line, I can use the line itself to estimate other points. So I'll look along the line for a point that I can identify pretty well. Usually we point this on a grid line. So let's see. Here's a point that actually looks pretty good. So I am at an x value of 5 and a y value of negative 140. So let's mark that down. Now that I have 2 points on my line, I can estimate my slope. So the derivative at 8 is the slope of the tangent line, and the 2 points on my tangent line are 5, negative 140, and 8, negative 320. So I can calculate the slope by taking the change in y, so negative 140 minus negative 320, and divide it by, notice I used, this is my first value, this is my second value, and so when I do x, I need to use the same order, 5 minus 8. So negative 140 minus 320, that's plus, so this is the same as saying plus 320, and so that is 180 divided by negative 3 equals negative 60. And so my derivative, the slope of the tangent line at x equals 8, we believe is negative 60.